Welcome to another episode of The Build Show. It's time for another deep dive. Today, we'll be digging into the two-dimensional scrolling API and building a simple grid view that lazily lays out its children while scrolling vertically, horizontally, and everywhere in between. While there are already 2D scrolling widgets available, today we're going to roll our own. This will entail implementing a custom render object. So if you have not seen the pilot episode of the Flutter Build Show, I recommend pausing here and watching that first. The 2D scrolling foundation arrived in Flutter 3.13, bringing with it many new, but hopefully familiar, classes for building widgets that scroll in both dimensions. Before we examine these, you may be wondering, why have a separate implementation for 2D scrolling when we can achieve 2D scrolling through composition? This is an excellent question. Flutter allows you to compose widgets together however you can imagine, including placing a one-dimensional scrolling widget inside of another. Composition like this can work, but in some cases it can create performance issues by laying out all of its children widgets instead of just those that are currently visible. The idea of only rendering the visible children in long lists is called lazy layout and is preferred for performance scrolling. Other cases of nested scrolling composition can create side effects like hidden scroll bars and missed scrolling notifications. For a better understanding of these cases, see the 2D scrolling preview video from Flutter Forward, linked below. It's for these reasons that we created a separate set of widgets and delegates for scrolling in 2D. First, let's start with a broad strokes overview of scrolling in Flutter, as the core components are largely the same for one- and two-dimensional scrolling. And intentionally so, since keeping track of two different systems would be quite the hassle. You may be familiar with the ScrollView widget, which scrolls in one dimension. This widget's primary job is to create the two core components of scrolling in Flutter, the scrollable and the viewport. The scrollable widget implements the interaction model for scrolling, including gesture recognition. It creates and manages the scroll position in response to gestures, which is then provided to the viewport. The viewport is responsible for the visual layout based on that position, what we actually see scrolling on our screen. I like to think of the viewport as a window through which you can see a portion of the scrolling content. These two core components are the same in the two-dimensional ScrollView widget. It creates the two-dimensional scrollable widget that handles the interactions, this time with two scroll positions, which inform the two-dimensional viewport, which then lays out what is visible based on the current scroll positions. This way, we only have one window for viewing our content, rather than two if we had composed multiple single-dimension scroll views together. As for what content the viewport displays, here is where these APIs differ the most. In a one-dimensional scroll view, the content is provided by slivers. We all know slivers. They are sections of scrollable content that are placed in a one-dimensional scroll view, one after the other. A list view, for example, uses a sliver list under the hood, just like a grid view boils down to a sliver grid. The lazy layout we mentioned earlier has always been handled by individual slivers. In two-dimensional scrolling, there are no slivers. Did you hear that? Let's roll that back and check the replay. In two-dimensional scrolling, there are no slivers. Okay, wow, I am glad we checked. Instead of slivers, the new two-dimensional viewport is directly responsible for laying out the children provided by the two-dimensional child delegate, which is similar to the sliver child delegate you may already know. We heard from Flutter developers that you want the ability to arbitrarily position children in the viewport. With slivers, each widget is expected to be laid out tightly aligned one after the other in the one-dimensional viewport. Their order, and thus their location, is determined entirely by their index, which helps with features like focus traversal and implicit scrolling. In the new two-dimensional viewport, children can be placed anywhere, unlocking all kinds of layouts. A single integer index, though, is insufficient in a complex array of children that scroll in all directions. While children can be arbitrarily positioned, we need a logical order for things like focus traversal. So instead of a unique index, children have a unique child vicinity, represented by an X and Y index to represent that logical ordering. We'll see this in action when we start writing the actual code. So now that we know all the players, how do we use them? You may have noticed many of these classes that we have been discussing are abstract. This is different from their one-dimensional counterparts for the sake of functionality and flexibility. As it turns out, the 2D foundation came to be during the development of a 2D scrolling table widget. The Flutter team conducted a user study to better identify the use cases, patterns, and expectations Flutter developers had. Based on the feedback we received in the study, we learned that many developers had already created and published packages that scroll in 2 dimensions. However, we also heard that feature completeness was a challenge. One package might scroll in 2 dimensions, but not support focus traversal. Another might have support for focus traversal, but not support diagonal scrolling. This was certainly in part due to a lack of support in the framework. So, we decided to focus on the fundamentals and build a robust 2-dimensional scrolling foundation capable of supporting all of the amazing 2D scrolling experiences we know you, the Flutter community, will build. This is why so much of the 2-dimension foundation is abstract. It handles focus traversal, implicit scrolling, garbage collection, adjusting the layout offsets for one or both reversed axes, setting up parent data, multiple modes of diagonal scrolling, or locking axes if that's what you would prefer, state restoration, primary scroll controllers, keep alives, keyboard dismiss behavior, hit testing, painting children, reordering children, and finally, backwards compatibility with existing scrolling conventions in the framework. So everywhere you may call scrollable.of or expect something to just work, it will, whether it scrolls in 1 dimension or 2. In the end, all you need to do to scroll some widgets in 2 dimensions is provide those widgets and their positions. So how do we do this? In this sample, we'll implement a grid that scrolls in 2 dimensions. Let's start from the 2-dimensional scroll view and work our way down to the 2-dimensional viewport where we'll implement its RenderObject, render 2-dimensional viewport. 2-dimensional scroll view is one of the abstract classes I mentioned earlier. Remember, the viewport is the primary workhorse for laying out children, and we are responsible for providing it through the build viewport method in this class. We'll stick a placeholder there for a moment until we implement that viewport, and for now, I will fill in all the super parameters for the constructor of our, let's call it, 2-dimensional grid view. Some of these may be familiar, like the cache extent, keyboard dismiss behavior, and drag start behavior, but others are new, like the main axis. Main axis is used to determine a lot of things in 2D scrolling. It is the axis that the primary scroll controller would associate with if primary were true, which defaults to axis.vertical. This also dictates order of precedence for things like focus traversal and painting. With a value of axis.vertical, children will be traversed in row major order, using the child vicinity, meaning we would traverse all of the x values for a given y before incrementing to the next y value. When the main axis is horizontal, this switches to column order traversal. Returning to our scroll view code now, are you looking for other familiar features like scroll controllers and scroll physics? These are wrapped up in a scrollable details class, so you can configure them for each axis of the 2-dimensional scroll view. Scrollable details even has vertical and horizontal constructors that can easily flip the axis direction based on the reverse parameter. The last bit of new API here is the delegate for our children and the diagonal scroll behavior. This defaults to none, meaning both axes will be locked, allowing scrolling to occur in only one axis at a time. Locking axes based on the weight of a gesture or allowing free movement in all directions are also options. From here, the two-dimensional scroll view will instantiate the two-dimensional scrollable, and we just need to provide the viewport. Ready to implement another custom render object? Let's make Craig proud. First, we'll need to extend the two-dimensional viewport, which is a RenderObject widget. Let's call it two-dimensional grid viewport, filling in all of the super parameters. The horizontal and vertical offsets here represent the scroll position for each axis, which is provided by the two-dimensional scrollable as it handles interactions that manipulate the positions. The axis directions tell the viewport which way we're scrolling, and again, the main axis tells the viewport in what order to manage the children. And finally, we have our child delegate and a few familiars like cache extent and clip behavior. As a RenderObject widget, this class won't have a build method and is instead responsible for creating and updating our subclass of render two-dimensional viewport, which we'll get to next. Let's call this yet-to-be-conceived RenderObject render two-dimensional grid viewport. Perfect. For creating and updating the RenderObject, we just need to pass in the parameters we received in the constructor. We also need to provide a child manager, which is a delegate used by the RenderObject to manage its children. But much of this is already handled for us. All we need to do is provide the context and cast it to a two-dimensional child manager. Now we can return to the build viewport method of two-dimensional scroll view and provide this viewport. It's time to get to the good stuff and implement our render two-dimensional grid viewport. Unlike the custom RenderObject episode, perform layout is implemented by the superclass, so it can do some things before and after we lay out our children in layoutChildSquence. We haven't created our children yet. We'll do that in our two-dimensional child delegate when we build our app. For now, let's suppose we are creating a grid of squares, all 200 pixels in size. First, I'll set aside some values we want to use. The pixels of the vertical and horizontal offsets represent where we are in the scroll view. The width and height of the viewport dimension is the size of that window we're viewing our content through. I'm going to add the cache extent to our viewport dimensions since I also want to render a little bit more than we can see, so it's ready to scroll into view. Doing so will improve the performance for more complicated widgets in our viewport by preparing the next row or two ahead of time. The two-dimensional child builder delegate provides the maximum X and Y indices for the child vicinities, which informs what vicinities we will call the builder with. I can use all of these values now to compute what children I should lay out. The calculations are pretty straightforward for a grid. I'm taking the total available space in the window and dividing by the size of each child to determine the number of visible rows and columns. I've stored these in the leading column, leading row, and trailing column and trailing row variables. Now that we know where we are and what we want to lay out, how do we obtain our children? The method that returns the child for a given child vicinity is build or obtain child for. The child manager then calls our two-dimensional child delegates builder with that child vicinity. And by the way, if that had already been built in the last frame, Flutter will reuse it. It is a really important distinction in the render two-dimensional viewport, as any children that are not retrieved through the build or obtain child for method or kept alive will be disposed of after layoutChildSquence. Now that we have our child, it is finally time to position it in our viewport via the layout offset, which is part of its parent data. We decided every child would be 200 pixel squares, and for now, let's just align them together. The last thing we need to do is tell Flutter the extent of the content outside of the viewport. Flutter uses this to determine whether or not this viewport has enough room to scroll, how to render the scroll bar, and stuff like that. The superclass will assert that apply content dimensions has been called here, so it would remind us in an error message if we forgot. Since we know how many children there are and we know what size they are expected to have, we can calculate the full extent of all the children and then subtract the size of the viewport to set the max scroll extent. So, we're ready. Let's get to writing our app with these classes. Let's have a material app with a scaffold and an app bar. And in the body of our scaffold, let's create an instance of our two-dimensional grid view, which requires that two-dimensional child builder delegate. For our case, let's specify a max x and y index of 9, meaning our grid will have 100 squares in it. For the builder, you'll find this is very similar to a list view using the builder constructor, only instead of a single index, we get that child vicinity. For each of these, I'll create a square-sized box and some text to help us orient where we are in the viewport. Maybe a bit of styling. We are on camera after all. Let's give this a spin, and now we have a grid that scrolls in 2 dimensions. Our grid is lazily laying out children on demand, reusing them when possible across frames, and taking out the garbage. And if you look closely, you can see other components of the framework working just as they should. The app bar's scrolled under behavior, which was added in Material 3, is triggered by the vertical axis progressing forward, but not the horizontal one. Let's tweak this a bit to see what else it can do. Remember when I mentioned the viewport would handle reversing the scroll axis automatically? Let's flip that flag on the scrollable details for each axis. As you can see, without having to modify our layout offset or child position, it's laid out correctly for the axis direction. This is part of the work the viewport does after layoutChildSquence, applying the axis direction to the normalized layout offset that we provided. This is super fun, but what if we wanted to make our grid a little more interesting by placing our children wherever we like all around this viewport? All of this is in our control to set the positions of our children however we like using the layout offset. Let's manipulate that layout offset to see this in action. I am going to update the layout offset of the parent data back in our layoutChildSquence method. Let's modify these values arbitrarily and just see what happens. While we're at it, let's also change up the box decoration on each of our children in the builder method of our child delegate. This should help us better visualize where these children are being placed and how they can overlap one another. I'll apply some opacity and borders as well as a new shape. Let's turn our boxes into circles, because why not? Running this shows we have created increasingly concentric circles, or a series of Venn diagrams that share more in common as we scroll by. And of course, they are all scrolling lazily in 2 dimensions. So that's how to create your own 2-dimensional scrolling widgets in Flutter. These APIs are still fresh and new. Even the Flutter team has only just gotten started building widgets on top of this foundation. If you haven't checked it out yet, the 2-dimensional scrollables package maintained by the Flutter team already has a table view widget, which can actually create our grid view example without all the code we just wrote. But we learned so much. The table view can also support pinned rows and columns, decorations, merged cells, and more. So check it out, linked in the description below. Table view even subclasses child vicinity to a table vicinity, which converts the X and Y indices to row and column nomenclature for even more convenience. The table view also provides great examples of extending the child delegates and parent data further for even more custom layout models, like the table cell delegate mixin and the table view parent data. I can't wait to see what you build in 2D. Keep scrolling, my friends, and for more on Flutter, as always, visit Flutter HQ at flutter.dev.